Alright, so today we're going to look at section 6.1 and 6.2, which is all about orthogonality. And so we need to remember a few things from back near the beginning of the course. Remember first that two vectors, u and v, are orthogonal if and only if their dot product is 0. And that's the first thing. Also remember we had this notion of an orthogonal projection of u onto v. So if I wanted to project u onto the vector v, so that's something like this picture. Here's u, here's v. The projection of u onto v is this vector right here. And we had a formula for that. The projection of u onto v is u dot v divided by v dot v, all multiplied by the vector. So those are some things from the past that we'll be using today. So first, let's notice something. So suppose that so this is going to be called an orthogonal complement. Complement with an E. Again, the root word is complete, so we'll see how that comes into play. But here's our idea. So we're going to let W be a subspace of Rn. And so our definition for the orthogonal complement is if W is a subspace of Rn, then here's our notation. It's W with a superscript, which is a perpendicular symbol. So this is and we say this W perp for perpendicular. All right, so then W perp is all vectors which are perpendicular to everything that is in W. All vectors V with u dot v equals 0 for all u in W. So W perp is every vector which is perpendicular to everything which is in W. So for a simple example, geometrically speaking, if W is a plane through the origin. And so if we've got a plane that goes through the origin, then what's everything that's perpendicular to this plane? Well, it's all vectors which go through the origin that are in this line, which makes a perpendicular line and makes a perpendicular vector with the plane. Right, so they have to go through the origin, remember, or else they're not a subspace. A subspace contains the 0 vector. So our plane has to go through the origin, and so must the line. And that's why there's only one such line. But so this line can go in either direction and go infinitely far. So this is W perp down here. If W is the plane, then the perpendicular space is the line. Here's my claim. If W is a subspace of Rn, then so is W perp. And so here's our idea. Zero is in W perp because for any u in W, u dot 0 is 0. And remember, this is our definition of being in W perp. A vector is in the perpendicular subspace, the orthogonal complement, if it dots to 0 with everything. But 0 dots to 0 with everything, so 0 is in W perp. So the 0 vector is in there. That's the first thing. Remember, it also needs to be closed under addition and closed under scaling. If so let's say if V1 and V2 are in the orthogonal complement, what does that mean? That means that that for all u in W, V1 dot U equals 0 and V2 dot U equals 0. So this is again what it means to be in the perpendicular in the orthogonal complement. That for any vector in W, this vector dots to 0 with U, and so must V2 because we're starting with two things that are in W perp. But this means that V1 plus V2 dot U, well, this distributes, so I get V1 dot U plus V2 dot U, which is 0 plus 0, which is 0. So it's closed under addition. I started with two vectors that were in W perp, and their sum also dots to 0 with any vector. So W perp is closed under addition. Similarly, it's also closed under scaling. If V is in W perp and C is in R, our scaling factor, then for all U in W, by definition, V dot U is 0, because V is in W perp. So for anything that's in W, V dots to 0 with it. But this tells me that CV dot U is C times V dot U. But that's 0, because V dot U is 0, which means that CV is in W perp as well, and it's closed under scale. So that tells me that W perp is in fact a subspace because it contains a 0 vector, it's closed under addition, and it's closed under scaling. Another definition. A set of vectors V1, V2 through Vn is called orthogonal. So the set as a whole is called an orthogonal set if any pairing of the vectors dots to 0. So Vi dot Vj is 0 for any I not equal to j. I can't have the same I and j because V, say, V1 is not perpendicular to itself. So these things are pairwise perpendicular. So let's look at an example. Here's my set. I would like to know if this is an orthogonal set. So I need to look at all possible ways of pairing these vectors up and seeing if they are orthogonal. But there's really only a couple, right? So I need to check this one and this one, the first and the second, the first and the third, and the second and the third. Since dot product doesn't matter what order you go, I don't have to change the order of these things. I really just need to say, well, what about 1, 2, 1 dot 0, 1, 2? If I dot those together, then I get 0 minus 2 plus 2, which is 0. I need to check the first and the last. If I do that, I get negative 5 plus 4 plus 1, which is also 0. And then finally, I need to check the second and the third. And if I do that, I get 0, minus 2, plus 2. So in fact, all ways of pairing these up make a dot product of 0. So these vectors as a set make an orthogonal set. This is an orthogonal set. How about this one? Well, I don't, again, we'll just start. Let's just check our pairings. Here's the first and the second. 0, minus 8, plus 1, which is minus 7, and I don't need to check anything else. No. As soon as I find two vectors which are not orthogonal, the set as a whole is not an orthogonal set. Okay, and so let's look at something else. So let's show that the following set is an orthogonal basis for R2. Okay, so we want to show that this is an orthogonal basis. Well, remember, what does it mean to show? How do I show that something is a basis? All that I would really have to do to show that something is a basis is to row reduce and show that I get the identity. And that's true here. When we row reduce, we get the identity. That means that it is a basis. That's true. So the only other part of this to check is to show that it's an orthogonal basis, but an orthogonal basis just means a basis which is an orthogonal set. And since I have only two vectors here, all that I actually need to do to check to see that this is an orthogonal set is to dot these two vectors together. But I get 12 and minus 12, which is 0, so it's true. So that's all that it takes to show that something is an orthogonal basis. Let's do something else here, though, that is a little bit new. Let's, part B, let's call this the basis B. Let's find the coordinates of x relative to the basis B for the vector x equal to 9 minus 7. Now, we can do this by row reducing, but I want to point out that in this case that there's actually a shortcut, a trick, that is helpful for some future things. So what does it mean to find the coordinates? Really what we're looking for, so what we're really trying to do is solve this equation. So we're looking for the scaling factors to put on these vectors. All right, that's what we're looking for. So let me call this B1 and this B2. All right, so we've got basis vector 1, basis vector 2. So what we're really looking for is x is equal to C1 B1 plus C2 B2. That's what we're looking at. All right, now here's the trick. And this is a trick that's going to work for any orthogonal basis. So we've got x is C1 B1 plus C2 B2. What if I took both sides of this equation and dotted by B1? So I'm going to dot this whole thing by B1 and then distribute it through to both pieces. Because it was an orthogonal basis, B1.B2 is 0. which means that I have a very nice formula. I can solve for C1 right away. C1 is just x dot B1 divided by B1 dot B1. And even if I was in higher dimensions, if x was C1 B1 plus C2 B2 plus C3 B3, the same thing would work. Because if I dotted both sides by B1, if I have an orthogonal basis, then B1 dot anything is 0 except for B1 itself. And so this formula is going to work in all situations, and I can actually say that C2 is still x dot B2 divided by B2 dot B2. And in fact, in general, we'll come back to the question at hand, but in general, if B is B1 through Bn is an orthogonal basis for Rn, then if I want to find the coordinates of a vector x relative to the basis, if I call that C1 through Cn, then C sub I, the ith coordinate of x relative to the basis b, is going to be x dot bi divided by bi dot bi. Exactly like we just found. So let's go back to our particular question. Remember, B was the basis 2 minus 3, 6, 4, and x was the vector 9 minus 7. So that tells me that C1 is x dot B1 over B1 dot B1, which means I have to take these two vectors as 18 plus 21 divided by B1 dot B1, which is 4 plus 9, which is 39 over 13, which is 3. And C2 is x dot B2 over B2 dot B2, which is 54 minus 28 divided by 36 plus 16. Um, 56 minus 20, yes. All right, so what's that give us? That gives us 26 divided by 52, which is 1/2. And we're done. So putting these things together, we found that the coordinates of x relative to the basis are 3, 1/2. And for us, while it may actually seem like it's quicker just to row reduce because we have a calculator, keep in mind that this is actually a much more efficient method, especially for larger dimensions. The calculator does it so quickly for us, but it takes a lot of calculations. And so if you're thinking about how do I do something really efficiently, because what I really have is a very large matrix or a large Rn with a very large basis, then as far as calculators and computers are concerned, this is actually the most efficient method to find the coordinates of x relative to b. Okay, so let's look at something a little bit different. Let's let x be the vector 2, 3, and we'll let u be the vector 4, minus 7. Let's express x as a sum of two vectors. Right, so let's find vectors a and b with each of these vectors are orthogonal. So A is orthogonal to B, and I want A to be in the same direction as U. So A is parallel to U. That's what I'm looking for. And the way it's worded makes it look, maybe sound a little harder than it is. As soon as I draw a picture for you, you'll see really all that we need to do. This is really our orthogonal projections from before. Right? So really all that I have is vector x. I've got vector u. I want to project x down to u, and this is projection of x onto u. And this is going to be our A vector, because this vector is parallel to u. It's in the same direction as u. And B is our other piece up here, the perpendicular piece. So B will be the this piece that's coming up here. So A is the projection of x onto u. And let's just find that first. I reminded you of that formula at the beginning. Projection of x onto u is x dot u over u dot u times u, which in this case becomes, so x was 2, 3, and u was 4 minus 7. So this projection is x dot u, which is 8 plus negative 21 over u dot u, which is 16 plus 49, all multiplied by the vector u, 4 minus 7, which is negative 13, and that makes 65. All times 4 minus 7, but that is minus 1/5 times 4 minus 7, which is negative 4/5, a positive 7/5. And so that's our vector A. So that's our vector A. And if we go back to our picture, our generic looking picture, we've got x, we've got u, we've got this projection down here. This is A. This vector here is going to be B. Notice that A plus B is x. Well, I know what x is, I got it. I know what A is, I got that. Which means that all that I need to do is solve for B. B is x minus A, which is 2, 3, minus this vector, minus 4/5, 7/5, which tells me that B is, so 2 minus 4/5, so that's 10/5 plus 4/5 is 14/5. And that's 15/5 minus 7 is 8/5. And so that's our vector B, which means that I can say that x is A, which we calculated up over here, minus 4/5, 7/5, plus B, which is 14/5, 8/5. This vector is in the direction of u, and this vector was perpendicular to u. One last idea, or notion here from this section. Which is the idea of an orthogonal matrix. And there's a little bit of a language trickery going on here. So, definition. a matrix is orthogonal if its column vectors are an orthogonal set and each of the column vectors is also a unit vector. And the trouble here is we say orthogonal matrix, and that makes us feel like all that should be required is that the column vectors are an orthogonal set. There's no real good reason for this, but this is just, for some reason, what everybody says. Everybody just, when they say an orthogonal matrix, they mean a matrix which is orthogonal, but also has unit vectors. And so this extra requirement of having a unit vector is sometimes hard to remember because it's not part of our word when we say orthogonal set. And so it's really something that just takes practice until we remember that that's really what it means. So for example, is this matrix, we saw this one already, or something close to it, is this matrix orthogonal? And the answer is no. The vectors are orthogonal. 2, 3, 2, 3, dot, minus 6, 4 is negative 12 plus 12, which is 0. So the vectors are orthogonal, but they're not unit vectors. So I may say something like, is this matrix orthogonal? If not, normalize the column vectors. And so when I say normalize the column vectors, what I mean is take each column vector and turn it into a unit vector that's in the same direction. That is, divide by the length. Right, so we're going to divide by the length. So we have 2, 3, and minus 6, 4. Well, the length of 2, 3 is the square root of 2 squared plus 3 squared. So we're going to have the vector 2, 3, and we're going to divide by its length, which is the square root of 4 plus 9. And so that's the square root of 13. So we have 1 over root 13 times 2, 3. This one, the length is square root of 36 plus 16, and we still have minus 6, 4. So this becomes, that's 1 over 52, square root of 52, negative 6, 4. So when I actually normalize, the matrix that I get is 2 over the square root of 13, 3 over the square root of 13. I just push this through to each piece. Negative 6 over the square root of 52, and 4 over the square root of 52. So I started with a matrix which had orthogonal column vectors, and I normalized it to make it now an orthogonal matrix. So now it's orthogonal. Because the vectors are orthogonal still. If I divide by the length, they're still in the same direction, so they're still perpendicular. But each of the column vectors is now a unit vector. All right, and that's what we got from 6.1 and 6.2. I'll see you next time.